You know, like you see qualities of your dad and your son. For me, it's like my mom never got to see me graduate high school. This is it. This is what I do. This is how I help people. We talk about these experiences because they're hard to talk about, but they are necessary.
Right. Dr. Joe Zundell, cancer is very mysterious, very difficult to talk about with any kind of absolutes, obviously. But things always change, and people really like to learn, like, what has changed in the last 5, 7, 10 years? That, along with, like, where have people's thoughts shifted? Like, sort of the evolution of thought.
Therapy space, in terms of making antibodies to kind of
30% off discount link and a $60 free gift when you use that special link down below. So think about being able to walk into a grocery store and immediately narrow down what you want. You want sugar-free, you want high protein, you want this. You can use these filters and shop for whatever you want. Plus, I also have my own signature products that I've created with Thrive Market. I've created some low-carb keto truffles that are sweetened with allulose. I've created nut butters that are sweetened with allulose, so like these dessert butters. I've linked out to them down below as well. But you can also just go to Thrive Market, our low-carb truffles, whatever. Anyhow, that link down below saves you 30% off your entire first grocery order and a free $60 gift. So if you're shopping, you're getting groceries for yourself, you've got to check them out. And they've been a big supporter of this channel for over half a decade. So thank you to them and thank you to you.
And then another space, radiation therapy, which has been delivered by, photon beams, which isn't exactly selective in some cases. You damage a lot of healthy tissue in the process. So we're learning a lot of new ways using things like antibodies to make radiation more targeted in killing cancer cells. So the immunotherapy space and radiotherapy or nuclear medicine, I think, are very...
So in terms of like very base level basics for people that are watching and people that maybe don't even know what immunotherapy is, can you give kind of just a 500-foot aerial view of that?
Sure. So our body, we make antibodies to deal with, tissue damage and pathogens, things like bacteria and fungi and various things in our environment. We can utilize the same aspects of our immune system by taking some of those antibodies, changing them chemically, molecularly, to target things that cancer antigens. And so we can engineer those antibodies somewhat synthetically work as opposed to something like a chemotherapeutic going into a cancer cell. So again, enabling immune cells to go into the proximity of a cancer cell and kill it. Specific types of immune cells like T cells, as an example.
Gotcha. So where would you say things have changed in that specific space from, let's just say, 5, 7 years ago to now, specifically with immunotherapy?
So we've gotten better at understanding the dosing and the efficacy of these drugs. Initially, when they first came out, we just thought it was going to, bring immune cells to the cancer cell and kill it with very little side effects. But we're learning that it can be too much of a good thing. So there's basically a condition where if you give an immunotherapy, you can get cytokine release syndrome, CRS. And that's basically you recruit immune cells to the cancer cell, and the immune cell, in doing its job, will secrete materials to recruit a hyperactivation of your immune system and damage healthy tissue. So we've learned that we need to mitigate or control that immune response over time using immunotherapies, even two years.
So from that sense, I mean, it was much more of correcting some of these other side effects that would happen as a result of immunotherapy. So when you say attack other tissues, so essentially you'd have a heightened immune response that would break down muscle tissue, break down what kind of damage per se?
It's more so just like chronic. It can induce chronic inflammation in a specific area, depending on where the cancer is, and affect the health of the tissue surrounding the cancer, the healthier tissue. And obviously you want to not do that. You want to just target the cancer.
Gotcha.
So that's, again, just keeping it as simple as possible for people.
Yeah, I know it's probably a very complex topic to go down.
It's really hard to control.
So it's in today's sort of cancer research with that, is immunotherapy used typically in tandem with other treatments? Is this something where, hey, maybe we've got sort of a chemical angle that we're taking alongside this immune angle?
Therapeutic, because cancer cells are very adaptive in the way that they approach certain situations. So sometimes when you combine a drug, an immunotherapy, because they're going to be different types of cancer cells that have different adaptations throughout a tumor. It's never just one type of cancer cell. So you can bring the immune cells to the area using an immunotherapy, target one subset of cancer cells that are upregulating a specific receptor or a cancer antigen. And then you can use a chemotherapeutic to target something else that's intrinsically different that the immunotherapy may not target.
Gotcha.
So some sort of different metabolic capability of that cancer. So it's kind of like you're attacking from two different angles. Like a two-pronged attack, like sending two different soldiers to attack at different angles.
Perfect. So when a cancer spreads, maybe to a different tissue.
Metastasis.
Yes. Does the immunotherapy change, or does the immunotherapy essentially stay the same? So is the cancer's DNA or whatever, and I'm not a cancer expert, so hopefully I don't know a lot about cancer at all. So hopefully I'm going to ask questions that people really get some juice out of. Because
for me to understand everything, even as a cancer biologist, which is why I focus on the basics of cancer biology, and even then it's not basic.
Yeah.
So
totally.
I don't expect you to understand everything, just as I don't.
Well, I expected you to know everything.
I don't.
And
I'm okay with that.
Okay. You got to go.
All right. See ya.
So when you do have this metastasis that occurs, and so does the immunotherapy stay the same, or does it change when the cancer is in a different tissue, or is like lung cancer that goes to the colon, is that still lung cancer, or does it become colon cancer?
So the things that change as a cancer cell metastasis are in disease. Because essentially, in order for a cancer cell to metastasize, it has to change specific characteristics about it to be able to differentiate to different tissue and be able to survive there. So you've probably seen that some cancers have a higher tendency to metastasize to specific organs. Like you mentioned, lung cancer metastasizes frequently to the colon, but also frequently metastasizes to the brain as well.
Yes.
Common metastatic sites. And there's a reason for that, because they can't metastasize to a lot of organs because they can't survive there. So they need to be able to adapt specific abilities to be able to very specific characteristics. Those characteristics I don't personally know because I haven't studied those molecular changes that occur. But from a metastatic perspective, it's almost like a new disease. So the treatments need to change to be able to accommodate metastasis, which is typically later stage in aggressive cancers. So those treatment options definitely change. We can't use the same treatment in addressing earlier problems.
Got it. So
and that's one of the challenges in the clinical space too.
So do you have to target, if you have lung cancer that's spread to the brain, do you independently target those with different therapies for each, or is it, so you really do have to almost have a separate plan of attack? So the more that you have now different prongs that you have to go after?
Yes, and this is often why we see reduced responses in therapy as disease progresses. Typically when something metastasizes, it changes the survival rate of that cancer very dramatically. So the earlier you can detect a cancer is going to be the better, because then you can treat it earlier in its development, and it doesn't have the time to adapt those or evolve those evolutionary characteristics metabolically.
So with immunotherapy per se, I can speak, from my personal experience with my father.
It targets EGFR.
Got it.
We spoke about this offline for those listening.
Yeah. So my father passed away of lung cancer that had spread to colon and brain, and talked about this drug that he was on that was highly effective for a period of time, for 6-7 years. He was given a couple of months to live, and then he ended up living for 6 or 7 years, 6.5 years after that. That sounds like that was an immunotherapy type. Is it?
Receptor, essentially to stimulate growth signaling, and it's upregulated or increased on the surface of cancer cells in many different types of cancers, lung cancer being one of them. And so we can give inhibitors to change the rate of reactions that occur downstream of, essentially you block the receptor from doing its job, binding to EGF, and essentially reducing those growth signals that come from that receptor, which stimulate cancer cell growth.
Very simple, direct things. Oh, if only you would do this, if only, Here we are 10 minutes into this conversation, and I can already appreciate just how utterly complex it is. This is not something that's as simple as, okay, well, reduce your carbohydrate intake and do this and that, which, I know we'll talk about a little bit later. It sounds like it's exceptionally complex. So how does, when someone looks at a cancer diagnosis, okay, someone comes in, they have cancer, what determines which route they go, whether they go radiotherapy, whether they go immunotherapy, whether they go this EGFR type medications? Like, what is the determining factor? Is it the stage? Is it the spread? What is it?
A lot of it depends on the stage and where it is. So if it's early stage, typically they'll employ some form of surgical method alongside a relatively, now we're learning, lower dose of a chemotherapeutic. But if it's later stage, it might be more beneficial to utilize an immunotherapy or radiation-based therapy. But again, that's going to vary between cancer type and also the patient, because we also have to consider quality of life at the same time, things that are not easy to understand regarding human physiology, nonetheless in a disease state.
Yes. Is there actually a risk to surgically removing cancer independent of anything else? I hear people talking, and I have no idea if it's true or not, that you can cause more spread if you go under surgery, go under the knife with even an earlier stage cancer that maybe...
I would say that it's very low risk to induce spreading. So
not like you cut open a tumor and it just opens up and spreads everywhere.
So you're talking about like you're cutting it open and then you're causing cancer cells to break off from that tumor, maybe get into circulation and go elsewhere. It's not, so metastasis is a very regulated process. So a basement membrane it's sitting on. So let's just say I'm a cell, I'm stuck to this chair. I need to change certain characteristics about myself as a cell to get unstuck from this chair, which means reducing the expression or maybe upregulating enzymes to cleave the receptors that are keeping me attached to this chair. And then also change characteristics once I'm detached from this chair to get through tissues or extravasate into tissues and get into the bloodstream. So this is a very time-dependent process that can't be achieved.
Got it. Okay. So
that makes sense?
Yeah. So I mean, and I'm sure it depends on the type of cancer, but it's, I'm sure there's a range of times, but it's not something that's happening instantaneously. It's not like it's a bunch of crawling bugs that are just going to go and, okay, I like this organ now.
Yeah.
Because I know, I mean, if you look, again, you talk to people online, like that's the kind of, well, that's also just kind of the knowledge that's out there. It's like, where have you seen sort of the research starting to go in the last couple of years?
What is the most promising area of research in cancer space? I would say, again, probably the immunotherapy space or our better understanding of cancer cell metabolism with...
So,
do you want an example of that?
Yes, I was going to say, give me an example.
Back in the day, in the early 1920s, Otto discovered essentially that cancer cells were fermenting glucose. There's no oxygen present. That's typically when cells will ferment glucose. So it was confusing for him to see that cancer cells were fermenting, named as the Warburg effect, and is a hallmark of cancer. It happens in most cancer types at some point in their development. And so initially the hypothesis there was that they take in more glucose, they increase the receptors that take in more glucose on their cell surface, and they have increased metabolic flux or rates through glycolysis into the citric acid cycle, into the electron transport chain. All of that to say that they produce more energy to keep cancer cells growing. So the assumption there was that all of this rate of glycolysis, citric acid cycle, electron transport chain was very fast. We're now learning that that was not true. Glycolysis itself, in newer papers we're learning, Dr. Caroline Bartman at UPenn now is an assistant professor, that showed very nice mathematical model that showed that in mouse models, again, that's an important emphasis, that Warburg's findings were supported very well in terms of glycolysis, very fast. They mathematical model to determine the rate of glycolysis in cancer cells, very fast glycolysis. But as they analyzed the rates of those intermediates through mass spectrometry, looking at the molecular carbon moving through glycolysis into the citric acid cycle, into the mitochondria and the electron transport chain, that it was very slow. So some of those key energy processes and be able to maintain their growth, like it's just counterintuitive. So cancer metabolism, I can say from this paper, is in general slower than we anticipated while still maintaining that initial Warburg effect in the glycolysis cycle. And again, a lot of this comes from technological advancements in mass spectrometry, being able to label carbon molecules and trace them throughout their metabolic processes. So what we've learned from that, and I'm sorry to go on a tangent
No,
here,
this is
but
great.
It's a very complicated paper, and other papers have supported this as well. What we've learned is that they'll increase the rates of glycolysis to go into other metabolic pathways to enable promoting of cell growth as opposed to just an emphasis on energy production via ATP. So it's energy redistribution more so.
Got it.
To be more favorable to cancer cell survival. So it is an adaptive response. And again, it is very complicated. That's me trying to simplify that. And I know it is very complicated.
So, I mean, you really are borrowing from Peter to pay Paul in that sense with cancer. I mean, it's like it's taking the fuel from here and putting it here. So
exactly.
In early stages, I would imagine that probably doesn't manifest in like much energetic difference at a like mitochondrial level in a healthy tissue, but at even a more progressed stage or fuel on hand, where even throughout this, sort of slow metabolism of glucose or fermentation of glucose,
there is a competitive nature of that. So yes, there are conditions. We utilize a small molecule inhibitor to target glutaminase, which enters glutamines into various cycles. If we use an inhibitor to target that enzyme, it's not going to be as effective as we initially thought. If cancer cells are slowing it down, it'll still be effective, but that actually might be more damaging to healthy cells around it because they're more likely to have increased rates of the citric acid cycle than the cancer cells.
It's
shifting a paradigm almost.
Totally. That's really wild. I mean, how has that changed how treatment occurred? The speed in which certain things are done. I mean, if we know, okay, if we once thought that cancer metabolism was very, very fast and this glucose fermentation was very quick and now it's slower. I mean, is that a good thing if that's correct or not? But
That's correct.
Is that not as time sensitive? Or when you say, hey, this process of how it feeds, when we're talking slower versus fast, right? A healthy tissue being fast, a cancer cell being slow, are we talking a difference in nanoseconds? What's
probably even less picoseconds.
Okay, so it's not like
hard to, from a scale of a treatment perspective, it's hard to address things in picosecond range. But timing is very important in terms of how we decide to treat a patient or eradicate cancer cells. From a clinical perspective, that's very challenging. And there's still a lot in that space that we still need to understand. Like we're just beginning to understand that these metabolic rates are affected because now we have mathematical models and technology to better understand them. Not only when we treat cancer, but how we treat cancers because of that when.
That is. And I know we're going to do a separate video on exercise and also how cancer cells eat specifically. But I mean, I'm very curious right now, like how much of this is demand driven versus say supply driven? So like if you have a cancer cell, and I'm just going to, this is probably scientifically inaccurate, but I'm going to do it to illustrate a point, a muscle cell and a cancer cell. And all of a sudden this patient becomes very active and they're sprinting. In the sense of there's metabolic demand, the muscle cell for fuel, is that going to potentially take priority? Like can these priorities shift or is it purely supply driven? If there's more fuel available, the cancer cell is just going to suck it up, whether there's more demand from a given tissue or not.
So now, and that's a great point, and it seems like you've read some of the papers on this maybe, but
that's just intuitive. I was just kind of thinking because there's a lot of stuff like
there's some research coming out which is examining, how we change the epigenetics of cancer cells, so they change their metabolic rates in certain situations. So like we'll talk about this a little bit more in maybe a different context, but like how diets, which examine like ketogenic diets in combination with chemotherapeutics, cancer patient health. But essentially by employing global metabolism in cancers, we can essentially provide a new window of opportunity to treat cancer cells by changing their metabolism from what they were before to be more sensitive to that other intervention that we're giving.
That's really
Does that make sense?
Yeah, it does make sense.
Okay.
It does make sense. So, I mean, you're doing this in a where I'm talking about it in like a literal exercise sense. I mean, you're talking about it like that's basically as a demand for energy sense.
Yeah. So even if we exercise, we can also change the metabolism of specific cancer cells. Of course, it's going to vary between where that cancer is. I don't know if exercise will change the metabolism of all types of cells to be more favorable to treatment options that are available.
That's really good.
Whether it's from an immunological perspective, we know in some research studies that exercise can stimulate the immune system to be more responding to cancers in combination with like an immunotherapy. So if we give a cancer patient like an anti-PD-L1 inhibitor, which essentially brings T cells to a cancer cell, enabling activation and killing of cancer cells by the T cells. T cell is a type of immune cell. coupled with exercise, it might increase the ability of that immunotherapy to do its thing, as opposed to if they didn't exercise and they just got the immunotherapy.
Well, so even with like while undergoing treatment, I mean, I know, and you're not an MD, so I'm not asking you to give patient advice here. But if so, I mean, you're not going to want to, at what point do you stress yourself so much that you...
Absolutely. Yeah. So I think that nowadays we're starting to understand more physical therapists alongside a chemo or a cancer patient's therapy regimen to help them exercise effectively to where they're not injuring themselves or potentially reducing the efficacy of the therapies that they're getting. Obviously, cancer. So those things need to be carefully tailored by qualified professionals. And realistically, I'm not one of them. All I can do is make suggestions about, getting help. Also getting somebody like a registered cancer dietitian, not just some nutritionist they saw online. Yeah. They need very tailored advice because, again, it's very different in a disease state than a healthy state.
For sure.
So we have to consider the types of exercises they're doing for mobility. If they've had surgeries, let's say, you have a breast cancer patient who's had breast tissue removed, their scar tissue, their mobility is not going to be as great as somebody who hasn't had that surgery or who, almost inextricably linked to muscle contractions. So their movement abilities are not going to be the same as a healthy person. So those things need to be taken into strong consideration alongside someone's treatment regimen.
Let's pivot a little bit more into your...
Currently.
Yeah.
I wouldn't say it's my area of expertise, but it is where I'm currently going because I want to see it be better.
Gotcha. Now, so pivoting there, how have things changed in the last 5 or 7 years in that specific vein?
Scientists are getting a little bit less afraid of working with nuclear or radioactive isotopes because there is an intrinsic level of fear that comes with working with radioactivity. No one wants to cause another Chernobyl. But working with radioisotopes is extremely well regulated in a clinical space and in a lab space. What I'm working on, without talking about specifics, is trying to make these things more targeted because previously, a therapy space, we're trying to mitigate the radioactivity building up in specific radioactive isotopes to either proteins or small molecules targeted directly to cancers in the same way that immunotherapies have been used.
So, I mean, for essence, targeting what? I'm assuming there's, just like in a healthy cell, you're going to have a nuclear receptor protein independently, or here's just a random example of something that I'm familiar with, like PPAR alpha, for example, and fat adaptation for, or even fat oxidation, right? Like you've got this nuclear receptor protein that travels to the nucleus of a cell, essentially tells that cell, do they often utilize the same sort of receptor proteins? Do they use the same transcription factors, or do they start kind of getting their own category of these things all together that have to be targeted? I don't know if that question makes sense.
No, it makes sense. So yes, cancer cells adapt their own programming to change the metabolics associated with how those transcription factors work. But from a radiotherapy perspective, it would be hard to target something like that because PPAR is inside the cell. Mm-hmm. So typically with radiotherapies, in the same way that we use immunotherapies, we want to target something that's outside on the surface of the cell. And then it can then be brought inside the cell. Good example. If we made an antibody that we conjugated a radioactive isotope to be targeted towards EGFR, which is increased on cancer cells, that would be a great therapy. I don't actually think that's been approved. I'll have to check that. But there have been other targets that are upregulated or increased on the surface of cancer cells that we've approved radiotherapies to. So that's a space that's improving.
So at the risk of sounding really naive here, is it almost like you're Trojan horsing this thing? Are you horsing its way in?
It's also more about the decay chain of that radioactive isotope. Okay. So even if it doesn't get into the cell, the decay, radioactive isotopes, getting into a little bit of the physics of this, they vary in their decay. So when they decay, they'll release materials that can get into the cell and damage DNA.
Okay.
Whether or not they're inside the cell, it doesn't necessarily matter. They just need to get there. And the type of radioisotope matters. So like using an alpha decayer is their ability to damage DNA and cause double-strand breaks than a beta isotope decayer, which would cause single chain. This is where we're trying to play with different isotopes, which might be more efficacious in the radiotherapy space. We're learning a lot about that now. And we're even using some for diagnostic purposes too. So you can change out the radioactive isotope to be less damaging to the cell and where the cancer is. And this is helping us to detect earlier stage cancers as well.
Yeah. I mean, they do this in, for matter of context,
Many of those
for
are
listeners.
approved.
Yeah. I mean, they do them in, they just did them in that, where they radioisotope labeled amino acids just to kind of see where they're going for muscle protein synthesis, right?
Yeah.
So it's like, I guess in those like small amounts. So, I mean, that's the kind of thing that you're saying is even in a muscle and performance type setting, we're willing to risk a little bit of,
Well, X-rays are technically safer than alpha irradiators. Their ionization potential is a lot weaker because of the quantum energy they exhibit.
Yep.
Is very different than alpha decayers.
Now we're getting into crazy territory.
Yeah, that's quantum physics.
Yes.
Which again, a lot of that goes past my understanding too.
It's just fascinating. So it's so interesting because like when you used to think that radiation was just you're beaming a laser at it and just trying to fry it, right? It's
and we are in some ways.
Yeah, but it's a much more calculated that's almost happening there. I don't want to say trickery is the word, but that's so interesting to me to find that we're able to do that.
Yeah.
We're able to say, hey, like, so when you talk about the rate of like a normal cell does, I don't know how that works, but it's basically getting just to the surface and then kind of penetrating weaker.
Yeah, basically. So they'll travel. It's more so that they travel as things are decaying, quantum molecules, neutrons or things as they travel through space, they can travel through stuff, no problem. But the rate of speed of those molecules traveling through space is going to vary, and that's where we're changing out radioisotopes to like an X-ray or a gamma ray because they'll just blow through stuff.
Exactly.
Yeah, like gamma rays will just literally blow through you. So their ionization potential is going to be a lot weaker than something that travels a lot slower and has a greater likelihood of interacting with atoms to smash them apart.
Is that why it's called like gamma knife? It's almost literally a knife. I mean, it's
kind of yeah.
Why is it called gamma knife then? Is it?
I didn't name it. I don't know the semantics there.
I've always thought like, okay, you got gamma knife or cyber knife, and it's like that's kind of what I visualize. I mean, when I hear that, I visualize like I
think surgical interventions, which that field of study has changed quite a bit too as we've begun to use lasers in terms of resecting tumors. Because before, if you're using a scalpel, the margins of a tumor, if you leave some of those cancer cells there, they can continue to grow. Now we're using more focused methods of surgical resection, dyes and those sorts of things, or chemically labeled dyes to be able to.
So when someone undergoes, let's say, oftentimes it's going to be a combination of chemotherapy and radiotherapy, you got it from two completely different angles in the hopes of kind of like diversifying your odds.
Usually it's two different angles.
Okay.
Yeah, they usually target two different things. DNA pathway overlap to some metabolic pathways. There's going to be, it's impossible. Two different things, even still there's some overlap just because of the overall nature of cell biology.
Now I have to ask, what prompted your passion here? Because you're one of the more passionate cancer biologists that I've ever encountered. I haven't encountered many, but it's just... Okay.
So when I was around 14 or 15, my mom was diagnosed with esophageal cancer due to a misdiagnosis, only a bit. I guess being Italian, eating too much of the red sauce can cause acid reflux. But they discovered she had esophageal cancer, and by the time they discovered it, it was relatively late in terms of disease progression. And as a 14 or 15-year-old, when your mom gets diagnosed with cancer, you don't know what to do. You feel hopeless. So the reason I got into what I have to be hopeless anymore, my entire studies have been dedicated to just, honestly, it was just an effort for me to cope with that loss. I just became addicted to finding out the why. And, I'm finding there are a lot of people in this health space that have very similar goals, like Max Lugavere lost his mom to, neurological diseases. And so that's my why, because I want to understanding, that a lot of things, were within my mom's control about her cancer. There's a lot of things that were just out of her control that, that's really why I want to try and educate people about what sort of things they can reduce their risks for cancer so that they can try and avoid it as much as possible. Controlling the controllable, so to speak. And so my whole journey has, just been, and also those people that are cancer patients know that they're not alone. because that's how I felt. It's an emotional topic.
For sure.
Yeah.
At what point in your life did you decide that you wanted to go this route? I mean, was it losing your mom?
I was 18.
Was it?
I was 18. I was angry. I was pissed off. Didn't know what to do. And learning was my only outlet. When I say I was addicted and I was angry and I was pissed off, if you had spoken to me when I was 18, you probably would have never spoken to me again. I pissed off a lot of people, rightfully so. Yeah. I was angry with myself and my approach, to say the least. So that's why I'm passionate, because I want those answers. And I'm very rigorous about how I get those answers, because that's how I impact this space.
Where was how has that impacted you as your
Sure. When my mom got sick, my mom and my dad got divorced when I was 7. So life hasn't been super easy for me in terms of the ups and downs. I have 4 siblings, 4 sisters. So that was an interesting hurdle too. Mm-hmm. I love my sisters to death. My dad and I haven't had the greatest relationship, because divorce, you hear one side of the story from your parents. When you're 7, you don't understand after the divorce. And we just kind of moved to a small town in Western Massachusetts. He was, but he was also not ethically sound. He had a lot of problems. But I have a good relationship with my biological dad now. We're good. As you get older, you learn more about the complexities of those situations. And, I was getting fed one side of the picture that, my mom and my stepdad fed me. So my mom, as much as I love her and she's my hero and I'll miss her dearly, she's got some faults too. Yeah. And you learn those complexities as you get older. And I learned that my dad wasn't the villain that my mom and my stepdad put him out to be. So my dad and I are good. My stepdad passed away. There's a lot of knowledge that was gained. When my mom got sick, my stepdad started a moving business called Gulf Coast Cargo, where we lived in Florida at the time, and we would move things up and down the east coast of the U.S. So I was, picking up boxes when I was 14, 15 years old. He'd take me out of school for weeks on end. And at that time, I was also in ROTC in school. I got commanding officer in my unit. They basically gave my scholarship to somebody else. I don't know how that budgeting happened, but I'm not surprised with the Army. Yeah. A different school entirely, and I had no money. Mom died. My stepdad abandoned me. And all I had was my sisters. And when I went to school, I was alone. Army took the money away. I transferred to the ocean. Actually, my goal was to be able to discover new organisms, to be able to isolate compounds to better treat diseases. Because you find some really interesting materials in extremophiles, organisms that have adapted to live in extreme environments like deep ocean waters. So I wanted to be able to purify some of those materials to be able to treat cancers. But obviously, the marine biology space is really hard to get into. I don't think there even is a space for that. Yeah. So the funding is very low. You're not going to do research in it.
To yours? In terms of just...
Cancer affects a lot of people differently. I wouldn't say that they're similar stories to mine, but there are similarly emotional stories. Everyone's got their different why. 8 maybe with cancer. It goes to, she was a stick figure. Yeah. Cachexia is in terms of muscle wasting that cancer patients typically exhibit. And that's, often kills more cancer patients than the actual treatment or the cancer. Yeah. So trying to combat that is another problem too. This is why we're also considering a lot of nutritional recommendations for cancer patients now too. We learn a lot over time. So everyone, again, going back to this question, everyone has their why. It's going to be different than mine. But because if I could get some of those seconds back with my mom, I would trade the world for it. No offense to anybody in my life. I would trade everything I have for that. Yeah. Just seconds. So if I can give that back to people, I would. Yeah.
No, it's pretty emotional for me too. No, I'm good. It was almost the inverse of your situation, in the sense that my mom and dad got divorced. I lived with my mom, had a close relationship with my mom, and from about 15 on was really on my own. And, that a lot of times meant financially too. And the reason that I didn't live with my father was because the relationship between my mom and dad was not good. And being on team mom for most of my younger part of my life, I didn't understand the person that my dad was. And so I went a lot of my teenage years not really having a relationship with my dad because I didn't know the person that he really was. So I go through life, and then he gets diagnosed with cancer. And a year or so into actually developing this relationship with my dad, where I realized he is a wonderful human being and an awesome dude, then he gets sick. And so there's a lot of anger there of just being like, I've been robbed of a relationship with this awesome person.
Yeah.
And there's a lot of frustration because he was actually really dealing with issues for a couple of years, similar acid reflux type thing. And that was the consistent diagnosis. You have acid reflux. You have acid reflux. Yeah. And I remember there was a point in time when he was, we were actually joking with him and kind of made fun of him. My dad was kind of a funny guy because he kind of was like, he was a very handsome dude. He looked like Burt Reynolds, but
you're still very handsome.
So, well, thank you.
You're welcome.
We did hug when Gabrielle Lyons told. Yeah, so
yeah.
I mean, yes.
Gabrielle Lyon, I did give Thomas a hug.
Yeah, so
for the record,
we used to joke with him because he's kind of like almost he looked like Burt Reynolds, but he was like deep down he was like a mix of Homer Simpson and Patrick Starr. Huh. It's like kind of, I don't know what this is, this acid reflux or whatever. I eat some ice cream and I feel good, and he was like eating this pineapple ice cream. I think he was in a lot of weird pain, and I remember the day I don't want to name names and throw anything under the bus, but
sure.
He was with a particular HMO on Medicare. Mm-hmm. He was able to go to a different doctor literally within a week of going on Medicare. They're like, you are riddled with cancer. And it's like, so prior to that, and finally, he gets I guess you'd call it a second opinion, but his Medicare kicks in and he goes to a different doctor. Mm-hmm. And and thus begins oh crap, it had already spread. So they're bad because that's really the bulk of the relationship that I had with him.
It's hard not to.
Yeah. So it sucks. And his treatment went extremely successfully. There was a lot of false hope, and I shouldn't call it false hope because it really was Davis. And I mean, they were even saying like, this is remarkable. Like he's responding so well. Lots of ups and downs.
Yeah. As it goes.
He's going to, this is amazing. This is amazing. And then eventually it was just, yeah. So that was a big turning point for me. And I'll kind of wrap it up with something that was, he was in hospice, and it was February 14th that my wife, February 14th, 2017, my wife and I found out that we were pregnant with our son. And
it's okay. Hospice sucks. I went through that too.
Yeah, it sucks. Let me get myself some sucralose to get me through this.
You want some fructose too?
Anyway, yeah, laughing always fixes it. Yeah. Cover everything up with humor. It works well.
That's what I've been doing.
So, yeah, we get there, and he always wanted to have grandkids, and he did have grandkids from his daughter, but they weren't I have a half sister, but they weren't super close.
Sure.
So he was really pushing for Amber and I to have kids. And I got a chance to tell him, on February 24th, I said, hey, you're going to be a grandpa. And 6 hours later, he passed away. So
at least he knew.
So we like to think that was kind of
it's time
he
to
waited
go.
for that.
Yeah.
Gave him permission. So it's weird because now it's like my son carries on so many characteristics of him.
Good.
It's awesome. So,
yeah, I mean, when my mom was with that is it's just a natural part of life. My mom was in technically a chemically induced coma when she was in hospice because her body just couldn't handle anymore. So we actually said, he took me to go do laundry, and the minute we got back to our house, which was maybe 6 minutes away, my sister called, just laying there. It's almost like you feel this went in a very different direction than I was expecting, but it's good. I think people need to hear this. It's almost like you can feel that something's not there. You know, and you always think about, for me, it's like my mom never got to see me graduate high school. And while I understand it doesn't make it any easier, by the time I finished my thesis in cancer biology, and my friends and family just standing there, man. My dad was there too, with my stepmom, incredible people, my mentors. And that was the first time since I was like 15 that I felt relief of that anger and rage. And that was a good feeling. That was the first time in a long time that I thought to myself, what do I do with the that I've been through? This is it. This is what I do. This is how I help people. We talk about these experiences because they're hard to talk about, but they are necessary. Humanity is complicated. There's no other way to sugarcoat that. We can't sit there and think that everything's binary, like everything is A equals B. These things are complex situations. And as such, there's a socioeconomic status, there's a psychological status of all these things that are associated with. So not only this is what I do, but this is what you do as well. Because I don't give a about any of that, no offense. I don't care about people to give back to people. So I'm sorry for your loss, but I'm not, in a way, because I think in many ways you and I wouldn't be here talking if we didn't have those experiences. There's a lot of good that can come from pain. Mm-hmm. And learning through that, I think, is super important. Without that pain, without that rage, I wouldn't have developed strategies to learn how to cope with that.
Yep.
Granted, it probably wasn't the healthiest way. Pissed off a lot of professors in my unwilling and unwavering wantonness to understand things. But throughout that, I've also gained incredible mentors that were just, they saw through all that and they were like, this person wants this bad. And I'll try and put them in a position of success to the best of my ability. Dr. Ian Duffy was a great undergrad. Dr. Rugang Zhang, my thesis advisor, we had butted heads many times, but a lot of these people saw the potential in me and helped me to be a better, more ethical, rigorous scientist and a better human being. Because at the end of the day, my science doesn't mean anything if I'm not a good human being as well. They have to go together.
Well, man, where can everyone find you?
Mostly I spend my time there.
Looking at cat memes.
With my cat memes. I love cats.
Yeah.
At Dr. Joe Zundell. I don't really use Twitter or X that much. It's not really an appealing platform to me. It doesn't allow me to be creative. So mostly Instagram. Have a Patreon if people want to donate. Again, I'll do this stuff for free till the end of time. But if they want to donate, they can go on my Patreon and give me $5 here and there. But yeah, they can find me on Instagram.
Perfect, brother. Thanks, man.
Thank you.